friction stir processing, a tool to develop novel functional materials. Experts are joined already, is with us, Dr. Arockia Kumar. And before I hand over this session to Sir, I would like to introduce about, I will give a brief introduction about Dr. Arockia Sir. Dr. Arockia Sir is Assistant Professor in Department of Metallurgical and Material Engineering from National Institute of Technology, Warangal, Telangana, India. He did his PhD in Material Science and Engineering from South Korea, and BE MTech from NIT Trichy, Tiruchirappalli, and BE from RCET Madurai. He has got huge teaching experience in NIT Warangal and also previously worked in RCET at Madurai. He was also a postdoctoral fellow in Japan and Korea, and senior research fellow at Tiruchirappalli. So he is a reviewer for the very reputed journals like Journal of Alloys and Compounds and Metals and Materials International. So he's organized so many workshops and actively involving in organizing various skill development programs like open source software, outcome-based activities, teaching methodologies for effective learning. And he has published so many international and national journals, publications in reputed journals, and he has been guiding he has been guiding at present 5 PhD students and many other MTech research scholars. So we are privileged to have Sir with us. Now it is the time for us to listen keenly about this session, and I think it will be great helpful. I request all the faculty members and research scholars, you please listen carefully so that you can raise any queries whenever you want to raise through chat box or after the session. So our session will be continued up to 1:30. After that, we will have a query session. So now I welcome Dr. Arockia Sir once again for this FDP, and I hand over this session to Arockia Sir. Sir, please.
Sir, thank you so much. First of all, I would like to thank Dr. P. Srinivas Rao for his kind invitation to present my talk in this FDP. So I would like to thank Dr. P. Srinivas Rao for this great opportunity to interact with the faculty of other institutes as well as the MTech and research scholars. So yeah, my title of the talk is Friction Stir Processing, a tool to develop novel functional materials. So the outline of this talk is going to be first to differentiate what's the difference between structural and functional materials. Then what is functional graded material, mostly the mechanical engineers and metallurgical engineers might have heard of these functional graded materials. So and then I briefly introduce friction stir processing, and then how friction stir processing is useful to develop or to produce or manufacture functional materials and functionally graded materials. And in our research group, so for about 5 to 6 years, so we are trying to develop some functional materials through friction stir processing. And I will be presenting those research data, and then through this, I would like to demonstrate how FSP is an effective technique to produce or develop functional materials. So that's the purpose of this talk. And and I believe this content of this talk would be really helpful or useful to the students. Particularly the students comes from our students are faculty, pursuing the research in the field of mechanical or metallurgical engineering. So for them, I believe that this content would be really, really useful. and to some extent to a physicist, like when I say functional materials, like how this will be, um, uh, how to convert a non-magnetic material into magnetic material. Yeah, so so there were some efforts to convert a non-metallic material into metallic material, sorry, a non-magnetic material into magnetic material through friction stir processing. So so there is some possibility in this direction. So to an extent it may be useful to physicists also. So um, first let us start with this, that is differentiate structural and functional materials. So structural materials are majorly used or studied primarily for their mechanical properties. The primary purpose of the structural material is to endure the load or applied force. So example is steel, aluminium. So for example, whenever you use a material to construct a bridge, so there the purpose of the material is just to endure the load and applied force. That force may be the load, or force may be a static or dynamic load, but the essential purpose of essential requirement of that material in this kind of application is just to endure the load. So whereas in case of functional materials, so that materials used are studied for their electronic, magnetic, optical or chemical properties. So in a simple word, other than mechanical properties. So there, of course, in any material in application, it has to endure certain load, and at the same time it is being expected to deliver some other some other function. Okay, thereby I can achieve two or I can achieve two objectives in a single material. So in that way it helps me to reduce the weight of that particular structure. Yeah, reduce the weight. So I don't need to look for a variety of materials to do a single function. So in that way, using functional materials is always an interesting one, and it's industry also looking for such materials, because when a same material delivers structural function as well as some functional property, it saves some money also. And also it reduces the cost, and then it also reduces the running cost. So there are so many advantages in that. So some examples are semiconductors, and then the kind of example which I am showing here through a picture. So this kind of a window material, so you don't need a sliding window. So by pushing a button, by aligning the molecules present in the glass, so either you can completely prevent the light or you can allow the light. So something like you are seeing here. So functional materials are always attractive. So and now let me introduce friction stir processing. What is friction stir processing? So it's a modification of friction stir welding process. So here I am showing two in fact two pictures here. That is so there is a material, there is a material 1 and then material 2, and then we are using a cylindrical pin tool. So in fact under this under this tool there is a pin. Yeah, and there is a pin. So as you are seeing here, this is nothing but pin. So this pin, what we are trying to do, we are trying to stir the material. Yeah, stir the material exist between material 1 and material 2. So thereby the material get displaced, and then the joining is established. So the conventional way of joining the material is you melt material 1 and material 2, let them mix, and thereby you are establishing the joint. We know that process really well. That is called welding. Okay, welding. But in this case, we are not taking the material to its liquid state. So we are entirely processing in solid state. So what is the advantage of processing the material in solid state? So because when you go to liquid state, suppose let us say at liquid state, the melt pool is good enough to dissolve gases from the atmosphere. So it may dissolve, and then while it is getting solidified, if those gases are not going out, and they may stay, and then they induce porosity in your joining. Okay, so that is one kind of disadvantage. And mostly whenever you are processing very fine grained material through fusion welding, then the kind of microstructure develops maybe little bit coarser than what you are starting with. In that way, the material properties suffer, or the joint you may get a poor property. Whereas whenever you process in solid state, so there is a severe microstructure refinement. So what do I mean by microstructure refinement? So that will be told you that will be told you in the due course of time. So here we are using a cylindrical tool to join, to establish a joining, to establish a joint. And that is friction stir welding. So what is friction stir processing? So like you just, instead of using this process to join the material, just you use you process this region something, or you process this. So you just stir the surface of the material. You just stir the surface of the material. Then you would refine the microstructure. So such a microstructure can exhibit different set of properties. Okay, and when such a microstructure exhibits a functional property, or how to make that processed zone to exhibit functional property, that's what going to be told in this talk. Okay, so and in this picture, so we are what are the general terminologies or nomenclature associated with friction stir welding. Okay, so whenever, suppose, let us say it rotates in anti-clockwise, so that means this side, this side, this side is called advancing side, and then the other one is called retreating side. And then this zone, this is called nugget, and then in general the processed region means this one. It takes a U shape. Okay, so this zone is nothing but a processed zone, and then the rest of the material which is unprocessed is called base material. And you have a tool, so that tool is having a pin, and then you have a shoulder, and this shoulder is always in touch with the material, so that the rotating of this tool generates a lot of heat, because this part of this shoulder is impinged on this surface, so that the severe heat, that severe heat generates as a consequence of this high speed rotation. It generates intense heat, and that plasticizes the material, and thereby the material is displaced, and thereby either the material is joined or the microstructure is refined. Okay, so this is how the process happens. And what FSP does, you may ask a question. Fine, I am taking a material and I am processing with the FSP. What it leads to? What do I get out of that? So the first one is grain refinement. So grain refinement. So you see the average grain size of this magnesium material here, whatever shown here, is around 780 micron grain size. And then after the FSP, so you see the grains are refined. So the average grain size is only around 25.6 micron. So in that way, you will be able to achieve severe grain refinement. You just imagine from 780 to 25 micron. So there is a strong severe grain size reduction. And if you decrease the temperature, if you decrease the temperature during the process, then what happens? You can achieve even the grain size less than 10 micron or less than 1 micron. And of course, it depends on the selection of process parameters. So the key thing is here is, first one is the grain refinement. And then next, you might have heard about alloy. Alloy is nothing but mixing of more than two or more than two elements. So in general, we are using alloys for any engineering application, because most of the time monolithic materials are very having very poor strength. So in order to improve the strength, I have to add some kind of alloying elements. When I add alloying elements, then it results in some kind of second phase formation. So sometimes we call them as a precipitate. And then, while like when you are solidifying it, so what happens, these precipitates are very long. Yeah, precipitates are very long, and then they are agglomerated, they are at one place. Now after FSP, what happens, you see these precipitates are disintegrated. Yeah, these precipitates are disintegrated, and then they are distributed in the matrix. So when for to achieve a good mechanical property, this is really required. So I don't want the second phase should be concentrated on a single phase, on a single location. It should be fine, and then it should be distributed throughout the matrix. Then only it will contribute to strengthening. Otherwise, it won't contribute to strengthening. Then what is the third one? So that is incorporate ceramic particles. So you take, actually, see, this is a single phase material. Yeah, so you have only simply, you have grains. And now what we did, we have incorporated silicon carbide particles into this. So like this, so these are all silicon carbide particles. So that means you will be able to make metal matrix composite out of FSP. So you'll be able to make metal matrix composites. So here ceramic particles are reinforced in the metallic matrix. So if you see all these things, so here you have refined the grain. So that means you have increased the grain boundary area. Yeah, grain boundary area. Fine. And then now here, so this is precipitate. Yeah, and then this one is matrix. So you have the matrix precipitate interface, right? So you see here now the precipitates are completely disintegrated. So then you have increased the fraction of interface area. Yeah, interface area is increased. Yeah, and here it is grain boundary area is increased. And then here once again you have created new interface, and you have also incorporated a new phase, that is nothing but silicon carbide. Yeah, so you have created new interfaces, and you have incorporated, you have brought one new phase. So that means now this material will have a character of both. That both means matrix as well as precipitate. So in thereby, so you get a combination of property, combined property of metal as well as ceramic. Okay. So and the final one, that is like dense dislocation structure after FSP. So you also create a lot of new dislocations into the material. So if you see all these things, these are all called crystal defects. Yeah. So these are all defects. So these defects means like grain boundary, and this is something kind of two-dimensional defect, and interface area once again two-dimensional defect. And then here also you are including a particle. Yeah, it has a 3 dimension. So it is a 3-dimensional defect, and you are creating new interfaces, that is called 2-dimensional defect. And here you have dislocations. This is a 1-dimensional defect. So these defects, these defects can contribute to strengthening of the material. Yeah, these defects can contribute to increase the wear resistance of the material. And now what we have to look for is whether these defects can contribute to any functional property improvement. Suppose if I want to improve some functional property, let us say damping, or let us say magnetic property or thermal property. So whether these defects can contribute to such kind of functional property. Yeah, that's what we have to look at it. So whenever a process is given to you, so whether that process helps to achieve the improvement in mechanical property, or whether the process can also contribute to some functional property improvement, that you have to look at it. But how to assess it? So you need to see what that process can give to you. So like that, in FSP can do all these things for you. It can it can introduce some new defects, and then the existing defects can be magnified, it can be multiplied. So whether these defects in some way will it be useful to improve the functional property, and that's what you have to look at it. Fine. Yeah, so whatever I have said just now, so that is like it is compiled in this slide. So you are like in a single phase matrix, you are refining the grain size, and you are reinforcing the particles, thereby you are making metal matrix composite. And then once again, the whenever a phase is redistributed, its interparticle distance is varied, and then it is distribution is completely varied. So whether what would be the effect of these things on the property, that's always the subject of investigation after FSP. Fine. So how this microstructural evolution happens? So when I say the grain size is decreasing during after FSP, and why it is decreasing? Okay. See, remember whenever you do FSP, you are importing two things into the material. So one is strain. You are importing a strain or deformation. Yeah. So you are importing certain amount of deformation. Then you are giving heat into the material. Yeah, heat into the material. Now let us see what these two will do to the material. So if you import strain and deformation, then it will create dislocations into the material, and it will change the shape of the material. And in FSP, there won't be a much change in macroscopic dimension or dimension of the sample. Dimension of the sample doesn't change after FSP. See, when you do rolling, there is a shape change, right? Suppose if you if you give a very thick block, and then by after rolling you are getting a very thin dimension. Yeah, you are getting a sheet. Yeah, right. So in extrusion, like in extrusion, like there's a larger rod, and then means the diameter is larger than the final one. Yeah, that you are changing the dimension. But in case of FSP, there is no significant change in the dimension of the sample. Okay. So then what happens? So we are importing some kind of strain into the material, and then that strain accumulates lot of dislocations. Now what you are giving additionally heat. How heat is generated? Because you are rotating the tool against the workpiece. Okay, so when it is being rotated, then it generates a lot of heat, frictional heat, and this heat, if this heat is good enough to to create recovery and recrystallization, yeah, recovery and recrystallization, then that would be really helpful to recovery and recrystallization process. And sometimes recovery, recrystallization, and it may leads to grain growth also. And sometimes what happens, if your material has precipitate, it may grow, the size of the precipitate may grow, or the size of the precipitate may decrease if the heat is good enough to dissolve the precipitate. Or if a material has no precipitates, and then it may the precipitate may comes into picture also if the heat is good enough. Of course, it depends on how much heat is generated, and then how long the material is exposed to that temperature. These things will decide whether the precipitate has to nucleate, or the precipitate has to dissolve, or precipitate whether it has to grow. Okay, so if you see, like in any welding, in any joining process, so you have a base metal region, and you have a processed region, that is nugget, and then like you have a heat affected zone, and then in FSP we have a thermomechanical affected zone. Why? Because we are importing a lot of deformation, so there is some thermomechanically affected zone. So we have one more new new zone in case of FSP. Fine. So now what are responsible for this microstructural change? In base metal, no microstructure change, but in other three there is a microstructure change. So what are the mechanisms responsible for that? So dynamic and static recrystallization, and of course recovery, recrystallization, and drain growth. So these are responsible mechanisms for the microstructural changes in the zone. And then if you have a precipitate, of course it nucleates, growth, and dissolve. Okay, so this is how the interaction between the heat and the deformation it is leading to recovery, recrystallization, grain growth, and this is the essential, essential mechanisms for microstructure refinement. So one has to understand. So see, we engineers, we engineer the microstructure. So, and by understanding the relation between the process parameter and what kind of strain and the amount of heat is imparting into the material, so you will be able to decide or you will be able to engineer the final microstructure. Now you take any process, yeah, it has some, it always comes with some set of process parameters. Okay, so similarly FSP also comes up with certain, some process variables. So we have a machine variable. So in the machine variable, like you have a tool rotational speed, it's a very important one, and then tool travel speed, and then tilt angle, and then plunge depth. Yeah, plunge depth. So these are some machine variables. Out of 4, these 2 are really important. So through various researches, people have established rotational speed and travel speed are really important. And then tool design variables, the shoulder. So shoulder diameter and then shoulder profile. Yeah, so what kind of profile it has, whether it is a smooth profile or you have a convex or concave surface. So it depends. Okay, like then you have a probe. So once again, the probe diameter is one variable, and then probe profile. So you see here, so like you have a threaded pin, a stepped spiral pin, and then you have a pin with some flutes. Yeah, so you have variety of pin morphology or profile, and then height of the tool. That is like to what depth you want to process from the surface, whether you want to process 1 mm, 2 mm, 3 mm. So how depth you want to process. Okay, then material properties. So mechanical properties and thermal properties. So whether the material is really soft or hard, or the material is able to conduct the heat quickly, or it takes some time. Yeah, so if it quickly conducts, then the material won't get exposed to high temperature for so long time, because it is being continuously dissipated. So in that way it will contribute to microstructural changes. If the material is having poor thermal conductivity, then you try to hold the heat at that place. Then the material will be exposed to high temperature region for a long duration, and thereby it will contribute to, once again, microstructural change. So this even material property also plays an important role in the final microstructure development. So, and here the earlier studies shows that tool rotational speed and tool travel speed has a great influence on the final heat. Yeah, so the amount of temperature develops in the zone. Okay, so T max divided by melting point it is proportional to, yeah, so the tool rotational speed and tool travel speed. Okay, tool rotational speed is playing a major role. Yeah, so deciding the rotational speed is a key. Yeah, and any process will lead to some kind of defects. You always need to optimize the process parameters in order to get a healthy zone. Healthy zone means without any defect. So here we have a wormhole, some kind of lack of penetration. Lack of penetration means that you are the pin doesn't go to the required depth, and then lack of fusion and surface lack to fill. So you get this kind of crack on the surface. So like this, we have variety of defects. Yeah, variety of defects in the material, and how to how to avoid those things just by optimizing the travel speed and rotational speed. So in fact, we have listed a lot of variables in the earlier slide, but if you ask what are the key processing parameters to get the healthy zone in FSP, so tool travel speed and tool rotational speed, these two are the key in getting a healthy zone. Other parameters, of course, they play a role, but their significance is minor. But this one is, these two are playing a major role. So for every material, you have to find this area. Yeah, so now it is qualitatively shown, but you need to, so if you are a researcher in this area, so if you are researching this area, first once you decide what kind of material you want to work, so for that material, what would be the optimized value of rotational speed and travel speed, that you have to seek for, and then only in that zone you can process and then further characterize the material. Now let us look at how composites are prepared through friction stir processing. Okay, so this is a monolithic material, and then now you are introducing some kind of reinforcement. Yeah, so you are introducing some kind of reinforcement or dispersal into the material. So this one we call is a composite. And what is, but through FSP, you will be able to turn the surface into composite. So we call it a surface composite. Why? Only part of the surface, part of the material, only surface of the material is turning into composite. Okay, the rest of the material is same as your starting material. So this is what called, surface composite. Okay, so this process is really good. The FSP is one of the in fact established method to produce surface composites. So if you suppose the disperse side may be like silicon carbide or alumina, okay, or it can be a tungsten or iron or nickel. So it can be a pure metal, or it can be a like silicon carbide or alumina or any ceramic particle. I mean, so titanium nitride, yeah, or boron nitride, yeah, boron. So you can boron carbide and then boron nitride. So you can keep this kind of you can import, you can reinforce this kind of ceramic particles into the surface. So but the conventional process casting, so it will convert the whole material into composite. So what are the methods to produce surface composite? So of course you can use arc welding, gas welding, powder spraying, laser hard facing. There are variety of methods to produce surface composite, and you have thermal spraying, CVD, PVD. So these are some existing processes. So here, like FSP in the recent time, in around 15 years time, so FSP has been used as an effective method to produce surface composite, and then it resulted in changing certain properties to a significant level. Yeah, significant. Fine. So how to prepare composites through FSP? One method is, so this is a as received aluminium plate, and then we are machining a groove. Yeah, we are removing aluminium, and then we are filling with reinforcement like this. You are filling reinforcement, and then you do processing. Yeah, once you do this processing, then you are getting processed zone. Yeah, so in fact this is nugget. Then the whole region is called processed region, and you can extract samples for for your further characterization from this processed zone. Of course, through wire cut EDM. So if the zones are really narrow and small, so you have to use wire cut EDM in order to extract samples from this processed region. Fine. So here, what this table summarizes. In fact, this table summarizes how mechanical properties, what kind of efforts have been made to improve the mechanical properties or tribological properties, wear properties of the material by constructing a surface composite. So people have used silicon carbide, they have reinforced silicon carbide, they have reinforced tungsten carbide, they have reinforced silica and titania, then molybdenum disulfide in order to improve the improve the tribological properties, or to increase the wear resistance by decreasing the coefficient of friction. Yeah, because we know that molybdenum disulfide is a good solid state lubricant. So by incorporating that, you will be able to improve the wear resistance by decreasing the coefficient of friction. Okay, if you see, mostly it is done on aluminum alloys. Yeah, aluminum alloys or magnesium alloys. So the works on titanium, steel are very limited because those are really hard materials. It is very difficult to process them through FSP. You need very sophisticated, you need very expensive tools. Yeah, expensive. For example, boron nitride tool, to process steels. People are using about, the cost of the tool is around 16 lakhs, just to cost of one tool, boron nitride tool. So whereas if you want to process aluminium, magnesium, zinc, so some soft materials and their alloys can be easily processed using H13 steel tool. Yeah, so the typical tool steel is good enough to process these materials. Hence, plenty of work is focused on processing aluminium or magnesium. If you see what kind of work have been done so far, majorly it is done to improve the mechanical properties. It is done to improve the tribological aspect. And some cases it is people have studied what happens to the corrosion property. These are the major focuses of the research. Yeah. So and then some people have incorporated single wall nanotubes, multi wall nanotubes. But after incorporating, what kind of studies have been done? It is to improve the how the mechanical property improves, how how wear properties are improving. So these are the focus. Yeah, so that people who are into this kind of research, so they have to know what kind of studies have been done so far, so that you can make a unique attempt in your research, and then so that you can go ahead with your research work. So that is the key here. But if you see that how this process is used to change some functional properties, it is very limited. Okay, and by adding any ceramic particles, naturally you are increasing the elastic modulus of that zone. Yeah, so because by incorporating this kind of ceramic particles, naturally ceramic particles have high Young's modulus as compared to aluminium. So if you take aluminium, magnesium, so their Young's modulus may be in the range of 40 to 80 gigapascal. Okay, magnesium and aluminium alloys. Whereas if you take the Young's modulus of silicon nitride, Young's modulus of silicon carbide, that used to be in terms of somewhere ranging from 200 to 400 gigapascal. So in that way, like by incorporating ceramic particles, you can increase the elastic modulus. And as I discussed earlier, wear resistance can be improved. Once you increase the strength or even you decrease the coefficient of friction, you can improve the wear resistance. Then, like some people try to improve the dynamic properties of the material by incorporating shape memory particles. So, and the key thing here, like where I want to, I want you to focus here is the purpose of my talk is like that how to make a non-magnetic material into magnetic. I want to make aluminium is a magnetic. Then what I can do, I can incorporate magnetic particles into aluminium. Thereby, I can make it magnetic material. Okay. So which process is really useful? Yeah, FSP would be is a nice process because it's a solid state process. So you can prevent the interaction between the particle and prevent the interaction between the particle and the matrix. Okay, thereby you can ensure that there is no interface development. Yeah, means interface. Of course, there will be an interface because whenever you have a particle and then this matrix, there is an interface. But whether that interface is deteriorating the mechanical property or not, whether that phase is unwanted or not, any reaction between the matrix and the reinforcement particle. So those things can be simply avoided by processing the material in solid state. Next is electrical conductivity. Okay, so you can add some second phase particles to improve the to enhance or lower the electrical conductivity. So for example, you take copper. Copper has 100% IACS, International Annealed Copper Standard. So that way, like if I want to improve the electrical conductivity of copper further, so I can reinforce with graphene. Graphene has 110 IACS. So by incorporating graphene into copper, you would be able to increase the electrical conductivity of the copper. Okay, so that kind of research can you can improve the some functional property. You see, so far we were able to change only the structural property, that is mechanical property or wear property, but there were some attempts to improve the or to modify the or to bring new properties into the material. Yeah, there is magnetic property, electrical conductivity, then thermal conductivity. So the second phase particles can be used to enhance or lower the thermal conductivity, and damping property. Like damping means vibration damping property. So you can improve the damping property, yeah, or you can bring you can improve it, or there may be some material which has very poor damping inherently. So you can improve the damping by introducing some particles particles where they are very strong in absorbing the vibration. Yeah, one good example is graphite. So as we know, so at least most of us are mechanical engineers, so we might have we know that our lathe bed, or you take any drilling machine or milling machine, so the beds are made up of cast iron. Why we are using cast iron? So because cast iron absorbs the vibration. And why cast iron absorbs vibration? Because it has graphite in the microstructure. So why graphite has to improve the damping property? Because it has a low Young's modulus. Okay, so its Young's modulus is only around 30 GPa. So whereas steel's Young's modulus is around 210 GPa. So by retaining carbon in the form of graphite in cast iron, so I am able to decrease the Young's modulus of cast iron to 130 gigapascal, because combination of steel and graphite overall, because graphite has very low Young's modulus, so the overall Young's modulus of your cast iron drops to 130 gigapascal. So thereby it becomes a good damper of vibrations. So like this, you can bring you can bring a new functional property to the material by means of reinforcement, and this reinforcement is in fact reinforced into the material by means of FSP. Fine. And so far I have talked about the basics of FSP, and then what are the process parameter, and then where you should focus on, means to develop a healthy zone, and then what are the efforts people have done so far. So that's what I have told so far. Then now we have attempted, so some of my research scholars have attempted to change the functional property of the material. So this is just to share our own experience with you, how FSP is good to alter the functional property of the material. So first let us start with high strength, high conductivity materials. So in many in many areas or many at many locations, we require high strength, high conductivity materials. So I want a material which exhibits very high strength, at the same time high hardness. And when I say high conductivity, high electrical conductivity, then copper is the good choice because it has a 100% IACS. Above copper, there is only one metallic material having high electrical conductivity, that is silver. Silver has 105 ISES. But can I use silver? No, because silver is very expensive. I cannot use it. So I have to go for copper. Now copper, so can I use copper everywhere? No, because copper is very soft. And if you see the hardness, it is only 40 Rockwell, like 40 HRB in Rockwell B hardness. So, and its strength is only around 210 MPa. But now I want to, for electric, for electrodes and then for switches, this kind of switch is being used in like locomotives. Okay, so we need to improve. Yeah, we need to improve the wear resistance of these plates. How to improve the wear resistance? Yeah, so how to improve it? So, like we have explored that whether FSP can do some help in this. Okay, so then we have we have collected the typically used high strength, high conductivity materials, that is copper chromium, copper zirconium, copper chromium zirconium, copper tungsten, this kind of like material. So in fact, we have bought this one from the market, we processed with the FSP, then we have seen how FSP improves. Yeah, at the same time electrical conductivity doesn't suffer. So is there any possibility? That was the focus of the research. And tungsten, so we have incorporated tungsten in order to improve the wear resistance at the same time without decreasing the electrical conductivity. Is it possible to manufacture such a composite through FSP? This is what we have investigated. So so the very first one is copper graphene composite. So as I told you already, copper has electrical conductivity of 100% ISES and graphene is 110 ISES. So by incorporating graphite into the material, so the result is if you see in fact what we have how we have incorporated graphene. We have incorporated the graphene by changing the travel speed, okay, and keeping the rotational speed constant. We just varied only the travel speed. So after processing a different travel speed, so we got very fine grain, okay, and graphite also reinforced in, not graphite, yeah, graphene also reinforced into the material. So you see, after doing FSP, you see how the wear rate is decreased. So initially the wear rate was here, and then it is drastically reduced after FSP. And you see how the grains, how electrical conductivity changed. You see the electrical conductivity was initially 98.5 ISES, because the kind of copper what we are using here is not pure copper. It's a commercial pure copper. So it may have some impurity. Then its electrical conductivity may not be 100% ISES. It may be less than that, because these impurity atoms or any impurity will hinder the movement of electrons. So thereby it will decrease the electrical conductivity. So that's why even the pure copper has around 98.5 ISES. But the key thing you have to note down here is, after doing FSP, what happens to electrical conductivity? The electrical conductivity decreases only around 1%. Yeah. So but my wear rate decreased multifold. So I was able to increase the wear rate significantly, but at the same time the electrical conductivity reduced. There is an insignificant decrease in the electrical conductivity. So like here we have achieved that our target. That's target is, I have to increase the wear resistance, I have to increase the strength, but at the same time I should not deteriorate the electrical conductivity to a significant extent. So that's what achieved through this work. Then copper tungsten composite. So sometime what happens, strength would be a predominant material selection parameter than the conductivity. So is it in fact by incorporating graphene, so you may not be able to increase the wear resistance enormously, yeah, because graphene itself, it is very soft. So we can incorporate tungsten. You see, in fact, powder metallurgy produced copper tungsten composite is one of the commercially successful high strength, high conductivity material available in the market. So we tried to construct such a composite through FSP, and thereby like the wear resistance once again brought down significantly. Sorry, not wear resistance, wear rate was brought down very significantly. That means we were able to improve the wear resistance significantly. But at the same time, you see what happens to the electrical conductivity. So electrical conductivity before incorporating tungsten is around 98.5, close to that. But if you see what happens to the electrical conductivity, it is almost retained. So without changing the electrical conductivity, I was able to improve the wear resistance by incorporating tungsten into copper matrix. So like this, FSP can improve the functional property of the material, or at least it helps to retain the functional existing properties, at the same time improve the strength. And next is the earlier research work was to play with electrical conductivity, but here what happens to vibration damping ability of the material. So in fact we have taken pure aluminium, copper, magnesium, and then we did FSP, and then we studied its hardness, microstructure, and then damping properties, vibration damping properties, using two different routes. Two different things. One is RFDA, another one is DMA. So and then we have taken some 6061 alloy, and then we have also produced some composites. Yeah, we have also produced some composites, and we try to study the damping properties. So in the beginning of my talk, I told you that what FSP does. So it introduces a lot of defects into the material, and defects can significantly contribute to damping, and that is the knowledge base. Yeah, so defects can, so for example, if you increase the dislocation, the damping may improve and at least up to certain value of dislocations. So these defects will contribute to damping. So when I'm able to bring some changes to the defect in the material by FSP, then it also affects the damping, right? So that's what we have investigated. So by processing aluminium, copper, magnesium, you just see like what kind of grain refinement achieved: 44 to 10, 20 to 4 micron, then 780 to 25 micron. So like this, we have varied the microstructure by means of FSP. Then what happens to the damping property of the material? So in fact, this is one of the this is one way of characterizing the damping property using impulse excitation technique or resonance frequency damping analyzer, RFDA. So what this technique tells us? So we are vibrating the material, yeah, and then we are just checking with respect to time how the material absorbs the vibration. Yeah, so now you see, so the material takes too much time to you are producing vibration, and then this vibration is being absorbed by the material, and then it comes to almost nil after certain time. Yeah, but you see how the FSP material absorbs the vibration. So it absorbs the vibration in a short time. Yeah, so that means what? The damping ability of the material is improved after FSP. That's the key thing. So we have changed the functional property of the material. Similarly, you see, so what happens to copper? So you are vibrating it. Yeah, the copper absorbs. Yeah, so it's almost it takes 0.4 seconds. But if you see FSP copper, So it absorbs in a very less time, almost half of the time. So thing is, you have improved the damping property after FSP. And in magnesium, you see, magnesium is a very high, is having good damping property. Like it's topmost in the metallic material. Magnesium's damping ability is really high, yeah, as compared to any other metallic materials. Okay, so like it absorbs so quickly, but after FSP, you see, so its damping ability, damping ability is decreased. So can I increase the damping property of the material by FSP always? No. It depends on the material. It depends on the material's initial microstructure. Okay. So that's the one key message I want to give. So the thing is, the summary of the slide is by increasing the dislocations, or in some material, increasing the dislocation would cause the damping to alter. So vice versa. In some cases, by decreasing the dislocations, you will increase the damping. But it is absolutely depends on the initial microstructure. So the important message is the damping property can be improved even by 2-fold or 2.5-fold by means of FSP. So that is at that whatever we have discussed at room temperature, and then what happens when I increase the temperature. So with respect to when you increase the temperature, okay, when you increase the temperature, the damping of the material naturally increases. Okay, but what is the difference between the FSP material and pure aluminum? You take this one is pure aluminum, yeah, and this one is FSP aluminum. So by just looking at the plot, you will be able to conclude that always this red color curve is after FSP. So the damping of a material, particularly at high temperatures, high temperatures, is better for FSP materials rather than unprocessed material. So that is about pure material research. Then we have incorporated graphite into the material. Okay, because as I told you already, graphite has very good damping property. So by incorporating graphite, you can improve the damping. And then, but graphite is very soft. So naturally, if you increase the graphite, then the hardness comes down. But anyway, our focus is on improving the functional property. So you just see at whether is at room temperature. So you see this curve is nothing but 15 volume% of graphite. Yeah, 15 volume% of graphite. So whether it is room temperature or high temperature, so you see the difference between the pure, not pure, as we call it a base alloy or base metal. So the damping property improved a lot, and even at high temperature also you just see so that properties are improved. Yeah, properties are improved after after FSP, and then also by incorporating graphite. Fine. So then we have done some more work, that is by incorporating silicon carbide particle. So you might have heard in recent time people trying to manufacture nanocomposites. So what is nanocomposite? The reinforcement is in the range of nano size. Okay, so people are incorporating. So previously, if you see, a lot of works in metal matrix composite. So usually they take silicon carbide or boron nitride, boron carbide in micron region. See, micron region means the particle size in this region, 9 micron to 109 micron. So the particles they used to incorporate, then study the properties. Yeah, how does the property change? But these days people are trying to incorporate particles of nano size. Thereby they are trying to achieve a microstructure with very fine grains. Yeah, sometime in terms of nano region. So such a structure would exhibit what would be the mechanical and damping properties. That is always interesting subject to interesting subject to study. Okay, so in this case, what we did, we vary the particle size and then we check how the particle, how it is contribute to damping. So by incorporating particles, so the average grain size is come down, and if you see what happens to the damping properties, so you see the improvement here. So if the particles are really coarse, then their damping would be really high. Yeah, very interesting result. That is, otherwise general trend is when it becomes so fine, then people may think that it may show a good damping property, whereas here larger the particle, better the damping properties. That was one of our contribution. And it doesn't mean that you have to include only ceramic particle as a reinforcement. You can include even pure iron and pure nickel. As long as these particles won't interact with the matrix and then produce some intermetallic phases at the surface, you can reinforce any metallic materials into aluminum or magnesium and steady its damping properties. So once again, the damping properties are significantly improved after FSP and as a consequence of incorporating the particles. Yeah, so you can readily notice this. So this is as received alloy. Okay, it takes very long time to isolate the vibration. But if you add aluminium iron or aluminium nickel, so you just see how it is stopped even at short time. So so far we have discussed about functional properties and then particularly functional properties of homogeneous material, composites. So now what we do, we discuss about functionally graded materials. Srinivas Rao sir, are you able to hear me?
Yes, sir. Yes, sir. Carry on.
Yeah, yes. So the functional graded material. So we always look for homogeneous properties throughout the bulk. So here, we are using nowadays we are looking for functionally graded material. So how does property changes? So in fact, the property of the functional material changes as you move from one end to other end. And if you see the composition, that also changes with respect to when you are moving from one end to another end. So there are two ways of changing. The property may gradually change. That's what you are seeing here. Gradually it may change, or it may be some kind of step by step. Yeah. So step by step the properties may change. Fine. Accordingly, so how to achieve that? So how to get in a single system, you want to get a multiple property. How to get? See, once again, so we are all mechanical engineers. We know that, you see, for example, you take the example of crankshaft. So where are gears? So I need very high wear resistance at the surface, and the core should be soft. Yeah, how to get such a microstructure? So how to get that microstructure? So we know that induction hardening, carburization. So by carburizing the surface, you are increasing the wear resistance, and the core is already in pearlitic structure. So you are getting a tough core. So that's a good example for functionally graded material. But there you have only two layers. But I want layer much more layers. How to get it? So because the modern technology expect that a combination of good stiffness, strength, ductility, toughness, everything I want in a single material. Okay, I want energy efficient, eco-friendly, minimal weight and then cost. So I want everything. I want best in everything. So how to achieve this? Of course, that's where we are preparing composite or functionally graded material. So how to prepare functionally graded materials? So that will be the subject in the due course of time. So before that, So I would like to present some of the success stories, how people have created or produced functionally graded material through FSP. So they have taken one 7 series aluminum alloy, and then they have incorporated boron carbide and titanium boride so into the surface. And then what happened, there is a a bullet penetration, and then they have just checked how deep the bullets are traveling, yeah, in this kind of plates. So unprocessed plate, the processed plate. So you see the depth of penetration is 37 millimeter when you are dealing with only 7 series alloy. But the depth of penetration significantly decreases. The depth of penetration of the bullet, in one case, it is only 20 millimeter. So by creating a functionally graded material, so see, but that the bullet first faces the composite layer, and thereby most of the energy is getting dissipated. As it travels in, your core is very soft, so that is being finally stopped. So at very very less penetration depth. So this is one good example. The FSP is a good tool to develop functionally graded material. And then next is once again the same kind of work in 7075 alloy, and now the reinforcement is boron carbide and molybdenum disulfide. And once again you see in the base metal depth of penetration is this much, whereas where you have 30 micrometer size boron carbide, the depth of penetration is this much. So, and the kind of hole you generate, so in the base metal you see how large it is, but in the FSP zone you see the kind of hole generated, it is very less compared to the base metal. So in this way, like you can there are some real success stories for developing functional graded material through FSP. So let me skip this slide also. So now how to generate such functionally graded material? So through FSP, so that, as I told you earlier, you can convert some depth of the material into composite, and thereby so this side is becoming more stronger, and then this one is tough, core is tough. The other way is just to refine the grains. How to refine the grain? So you process the zone with different depth of the the pin depth is different. So here it is 8 mm, 6 mm and 4 mm. So first you process with 8 mm, then you process with 6 mm, then you process with 4 mm, or vice versa. First you process with 4 mm, then 6 mm, then 8 mm. That means the very first layer, it is processed 3 times, and the second layer processed 2 times, and then third one is processed 1 time, and then this is your base material. So thereby you have produced the gradient of microstructure. For example, this is base material, and this zone is processed let us say twice, and sorry, one time, and then this is processed for 2 times. So then you get very fine grain here, and then somewhat coarse, somewhat coarse grain. So here the base metal retain the core structure. So as you move up, you have fine grains. So such a microstructure can be developed using FSP by doing this kind of thing. So you have generated very fine grains. And it would exhibit high hardness, uniform corrosion, enhanced wear resistance. So all these things is the property of that. So then we know that there are a lot of process variables for FSP. So let me tell you one thing, that is I already told you there is an advancing side and retreating side, and the key thing here is the advancing side microstructure is different from retreating side. That is the key here. So when you want to develop a material with homogeneous properties, you have to choose the process parameter in such a way it doesn't result a much variation. But when you want to develop a functionally graded material, then you choose the process parameter, which will result in extreme variation. Yeah, which will result in extreme variation, and thereby you will be able to generate a gradual change in microstructure. So in the advancing side, we'll have a different microstructure. Retreating side will have a different microstructure, and thereby you will be able to produce a functionally graded material. So in a single process, with a single run, you will be able to generate a very nice, yeah, like a graded material. And then one simple thing is you drill a different size hole, you can accommodate more amount of reinforcement particles. Then you do frictions processing. After you do friction state processing, then this portion will have lot of reinforcement as compared to this portion. So thereby you will, there is a variance in gradient of distribution of the particles. So otherwise, what you do, like here whole depth is varied, here whole diameter is varied, so you can accommodate more amount of reinforcement. Then this portion used to be, it used to have a very high hardness as compared to the other side. So thereby you will be able to produce a gradient microstructure, and thereby you will be able to vary the property in a gradual manner. So in summary, friction state processing is a solid state process, and it's a green technology, green technology as compared to some of the existing welding techniques. And people have proved the amount of energy you spend in friction state processing may be slightly lower than what are the existing process, and there is no emission of gases during welding process. You don't need any special gas atmosphere. So in that way, this technique is eco-friendly, and it's a very nice process to engineer the microstructure, not only to improve the mechanical properties. There is a great possibility for improving the functional property, and this presentation has addressed. So what are the successful efforts in improving the functional property, in producing the functional property through FSP. Okay, and there have been the methods to produce functional property through FSP have been developed over the period, and it is up to us to utilize this process to improve or to bring new functional properties into the material. So with this, I would like to sincerely thank Dr. G. Madhusudan Reddy and Dr. Ramarao, Dr. Chakravarti, Dr. B.K. Nayak, Venkateshwaran, and Mr. Vidish Nayak, so for their help and assistance and guidance in conducting some of our research work. So I wish you all a very happy and productive time ahead, and I would like to thank the participants of this FDP and the organizers for giving me a great opportunity to share. So with this, I would like to thank all, and then now, so I request you to come up with some questions. Thank you.
Yeah. Thank you very much, sir. Thank you very much for taking nice and informative session. We are privileged to have the experts like sir from IITs and NITs. Yeah. So now it is the time for queries from participant side. If anybody has any queries regarding this session, so please you are free. You are free to ask the questions, or you can do. You can ask the question through chat box also if you have any queries. Okay. I think you have understood the questions. You have understood the sessions very well, and I hope you are not having any questions. You can contact sir also through mail or a contact number that has been given in NIT Warangal website. If you go to Metallurgical and Material Science Engineering Department, you will find sir's contact details. If you have any other doubts, or if you want to carry out the research in this particular field, you are always welcome. I think sir will be available. है ना? So thank you, sir. Thank you for thank you, sir, for giving us your valuable time. So thank you all once again for joining. So thank you.